Hello friends, welcome to this lecture on microprocessors. As we have seen various units up till now, we have seen introduction to mechatronic systems, we have seen studies of sensors, transducers, we have seen control systems, we have seen some actuating elements like hydraulic elements, pneumatic elements and electrical elements. Now we are into this unit number 4, which includes study of microprocessors, microcontrollers, and programmable logic controllers. Out of these three important elements, as I said, microprocessors, microcontrollers, and programmable logic controllers, we'll be discussing microprocessors briefly. Briefly because out of the 6 units, this unit is a bit heavier in a sense. The electronics and telecommunication students study this microprocessors as a whole subject. They study microcontrollers as a whole subject, and they study programmable logic controllers as a whole subject. And all these three elements are included in a single chapter. In that sense, it is a bit heavier. So we'll be having introductory treatise only from mechatronics point of view. What is the relevance of microprocessors, microcontrollers, and programmable logic controllers? Briefly, we'll be discussing. Those who are interested in in-depth knowledge of microprocessors, microcontrollers, and programmable logic controllers, on YouTube, we have got wonderful video lectures available. On NPTEL also, we have got very good lectures. And on our AGPIT e-learning channel itself, electronics department have faculty members have posted very detailed, nice lectures on microprocessors, microcontrollers, and programmable logic controllers. You can refer lectures by Ligade sir from ENTC department or Jirge sir from ENTC department. They already posted these lectures on microprocessors, microcontrollers, and programmable logic controllers. In the department e-learning details, you can find out those lectures. And as far as our curriculum is concerned, you can refer Bolton's book, that is well and good. Or there are other Indian author books as well. One book by Rajput on mechatronics. He has dealt much in details on these topics of microprocessors, microcontrollers, and programmable logic controllers. Now, I have borrowed these presentations from electronics faculty only, and I have tried to make it as simple as possible and as brief as possible. And as I said repeatedly, you can refer the lectures from electronics and telecommunication faculty for gaining more knowledge. If you want to have some projects related to microprocessors, microcontrollers, and programmable logic controllers, they have those kits, and those faculty members will be in a position to help you out much more in details, because they have these subjects dealt in details, right? So we'll proceed further. In microprocessors, we'll be studying out of various microprocessors. We'll be studying the basic one, that is 8085 microprocessor. We'll be studying briefly. Now, as you can see, right from 1971, this revolution in semiconductors took place, and with the advent of development of large-scale integrated circuits, VLSI, very large-scale integrated circuits, the processors became efficient over the period of time. So initially, number of transistors used were 1,000, and the series of the microprocessors was 4004. And thereafter, when 10,000 transistors were used in 1974, that series was 8080 and 8008. Thereafter, in 1982, we have these developments of 8085, 8086, wherein 1 lakh transistors were used on a chip. And thereafter, you had this 80 advanced processor, that 80286, we used to call it as extended technology XT, and then advanced technology 80, and then 486, and then Pentium series with 80586 microprocessors, which were using somewhere around 10 lakh uh, transistors. And then we had Pentium 2, Pentium 3, Pentium 4, right now Pentium 5 with multi-core technology. So they're using millions and millions of transistors. So this development is going on continuously. This is how these microprocessors evolved over a period of time. This we already discussed earlier in the initial chapters. A 4-bit is called as nibble, and 8-bit is a byte, 16-bit is a word, and 32-bit is a long word, right? Just refreshing. Internal structure and basic operation of a microprocessor. This is what is called as arithmetic and logic unit. We have a register section, we have control section, and a timing section. These are the basic sections or basic units of a microprocessor. And then you have the connecting buses. Address bus will be there, and the data bus will be there, and control bus will be there. And these will be interacting with various elements of microprocessor so as to give us a meaningful output. Now, to start with, we have arithmetic and logic unit, the component that performs the arithmetic and logical operations. It's called as ALU, the most important component. It is one of the most important components in microprocessor. It's typically the part of the processor that is designed first. It is able to perform the basic logical operations like AND operations and OR operations, including the addition operation. The inclusion of inverters on the inputs enables the same ALU hardware to perform the subtraction operation, adding an inverted operand, and the operations of NAND and NOR. So these logical operations also this ALU is able to do. Then we have a control unit, the circuitry that controls the flow of information through the processor and coordinates the activities of the other units within it. It's called as a control unit. In a way, it is the brain within the brain. Now, microprocessor itself is a brain. So it is a brain within a brain, as it controls what happens inside the processor, which in turn controls the rest of the personal computer when it becomes part of a computer. On a regular processor, the control unit performs the task of fetching the data, decoding the data, managing execution, and then storing the results. So all these are the functions of my control unit. Then we have internal structure of the control unit. So we have the clock, we have the control step counter, and then we have encoder, instruction encoder, and then status flags will be there, and condition codes will be there, and the control signals will be generated accordingly. So this is how is the internal structure of a control unit. Then we have the register sets. Memory sets, you can call them, as the register section or register array consists completely of circuitry used to temporarily store data or program codes until they are sent to the arithmetic and logic unit, or to the control section, or to the memory. Temporary storage device are registers. The number of registers are different for any particular central processing unit CPU, and the more register and the register CPU have the more the registers in the CPU have will result in easier programming tasks. Registers are normally measured by the number of bits they can hold. For example, an 8-bit register or a 32-bit register, right? So these are the register sets. Then we have an accumulator, a register in which intermediate arithmetic and logic results are stored. It's called as accumulator. Example of accumulator use is summing a list of numbers. The accumulator is initially set to 0. Then each number in turn is added to the value in the accumulator. Only when all the numbers have been added is the result held in the accumulator written to main memory or to another non-accumulator or CPU register. This is the function of your accumulator. Then you have a program counter. A 16-bit register used to store the next address of the operation code to be fetched by the CPU. Not much use in programming. Counter does not have much use in programming, but as an indicator to user only. The purpose of program counter in a microprocessor is to store address of top of stack to store address of next instruction to be executed. It also has a function of counting the number of instructions and to store base address of the stack. For stack pointers, the stack is configured as a data structure that grows downward from high memory to low memory. At any given time, the stack pointer or SP holds the 16-bit address of the next free location in the stack. The stack acts like any other stack when stack is nothing but a pileup of the information, right? And when there is a subroutine call or an interrupt that is pushing the return address on a jump and retrieving it after the operation is complete to come back to its original location. This is a function of your stack pointer. Then you have a data bus. The database bus is bidirectional. It can send signals and it can receive signals. Data or instruction codes from memory or input or output are transferred into the microprocessor. The result of an operation or computation is sent out from the microprocessor to the memory or input and output. Depending on the particular microprocessor, the data bus can handle 8-bit data or 16-bit data. Then you have address bus. The address bus is unidirectional, over which the microprocessor sends an address code to the memory or input or output. The size of the address bus is specified by the number of bits it can handle. The more bits there are in the address bus, the more memory locations a microprocessor can access. A 16-bit address bus is capable of addressing 64K addresses, 65,536 addresses. A 16-bit address bus. Then you have a control bus. The control bus is used by the microprocessor to send out or receive timing and control signals in order to coordinate and regulate its operation and to communicate it with other devices. That is, communicate it with memory or input and output. So that is a function of your control bus. Then the microprocessor clock is also an important element. It is also called as clock rate, the speed at which a microprocessor executes instructions. That is the clock speed. So higher the clock speed, and now you must have seen in the computer specifications, you have the processor having clock frequency of 1.2 gigahertz, isn't it? 1.4 gigahertz. So 2.3 gigahertz. Higher the clock frequency, the faster is the processor and the faster is the computer. So it is the speed at which a microprocessor executes instructions. Every computer contains an internal clock that regulates the rate at which instructions are executed and synchronizes all the various computer components. The CPU requires a fixed number of clock ticks or clock cycles to execute each instruction. The faster the clock, the more instructions the CPU can execute per second. The clock speeds are expressed in megahertz or gigahertz. Some microprocessors are superscalar, which means that they can execute more than one instruction per clock cycle. Like CPUs, expansion buses also have clock speeds. Ideally, the CPU clock speed and the bus clock speed should be the same so that neither component slows down the other. So there should not be any loading effect, so to say, as such. In practice, the bus clock speed is often slower than the CPU clock speed, which creates a bottleneck. This is why new local buses such as AGP have been developed. Examples of microprocessors: Intel Intel manufactured Intel 8085 and Intel manufactured Intel 8086. Out of that, we'll be focusing on 8085. Intel 8085 is an 8-bit microprocessor introduced by Intel in 1977. It is also called as Intel 8085 AH processor, produced from 1977 to 1990. Common manufacturer Intel and several others. Maximum CPU clock rate 3.3, 5, and 6 megahertz. Instruction sets pre-86, right? Thereafter, we had 286, 386, 486, and 586, right? Packages 40 pin, right? So these 8085 has 40 pins. It was binary compatible with the more famous Intel 8080, but required less supporting hardware, thus allowing simpler and less expensive microcomputer systems to be built. So internal architecture, this you have to remember, you have to replicate in your exams even. As I said, it will be having a few registers, as you can see, B, C, D, E, H, HL registers and stack pointers, program counters, and then you have registers, temporary registers, some flip-flops, some accumulators, and then some instruction registers as such, and then timing and control circuitry. You have address buffers, and then you have data/address buffers, right? So each pin location has specific tasks, right? Those pin details we'll see in the next slide. As I said, 40 pins. Some pins are allocated for address alone. Some pins are allocated for data and address, right? As you can see here, E1 to A6 are meant for address, is 87 to next 89. These are address and data. And likewise, each pin has a specific task to be given. Then you have instructions and then serial input output control. Now this is called as the register array. So this is the internal architecture of 8085 microprocessor. Even in Bolton's book, a nice diagram is there, line diagram is there. You can refer that and you can remember that. What is the function of each pin? This is also called as a pin out or pin diagram. As I said, 40 pins will be there, 1 to 20 on one side and 21 to 40 on the other side. VCC is the supply voltage that is given to this processor chip. Then you have reset pins, you have address pins, 12 address plus data is 80, right? 12 to 19 address pins, and then address alone, maybe 21 to 28 address alone. Then we have reset, you have clock out, hold, and then you have traps, you have reset out, right? So each pin has a specific task to be. This also you have to remember, and you have to describe the functions of each pin. As I said, Bolton's book has got very good pin diagram that is given for 8085. Now let us briefly see what are the instruction sets of 8085. An instruction is a binary pattern designed inside a microprocessor to perform a specific function. That is called as instruction. The entire group of instructions that a microprocessor supports is called instruction set. 8085. Remember, 8085 has 256 instructions. Each instruction is represented by an 8-bit binary value. These 8 bits of binary value is called opcode or instruction byte. Operational code or instruction byte. Now, classification of instruction sets. You have data transfer instruction sets, arithmetic group instruction sets, logical group instruction set, branching group instruction sets, and stack and machine control group instruction sets. We'll briefly see few of the instructions, not all, few of the important instructions, and we'll try to understand. First, data transfer instructions, friends. These instructions move data between registers or between memory and registers. These instructions copy data from source to destination without changing the original data. So the first data transfer instruction is MOV, that is movie. MOV is the opcode for that, and the operands will be RD, RS, M, RS, RD, and M. The instruction copies the contents of the source register into the destination register. contents of the source registers are not altered. If one of the operands is a memory location, its location is specified by the contents of HL registers. Number of byte is 1 byte. Example is move B, C or move B, M to memory locations. Either register B to register C or from register B to memory M. MVI, move immediate, right? So this is MVI, move immediate. And this is the example. You can go through these details, and then you have LDA, that is load accumulator. It's a operand is 16-bit address. The contents of memory location specified by a 16-bit address in the operand are copied to the accumulator. It is a 3-byte instruction. The contents of the source are not altered. This is very important. LDA 2000H is an example of this command or this instruction. Then LDAX, that is load accumulator indirect. Operand is B/D register pair. Load accumulator indirect by using memory pointer. Okay, the contents of the designated register pair point to a memory location. This instruction copies the contents of that memory location into the accumulator. It is 1 byte. The contents of either the register pair or the memory location are not altered. So how it is defined or how it is represented? LDX or LDAX D. Then LXI, load register pair immediate. An operand is registered pair 16-bit data. This instruction loads 16-bit data in the register pair. It is 3-byte instruction. Example is LXI-H, 2030H. Then LHLD, load H and L registers direct. LHLD, it is operand is 16-bit. Address is to be given. It copies the contents of next memory location into register H. It's a 3-byte instruction. So LHLD 2030H is an example. Then we have STA, store accumulator direct. The contents of accumulator are copied into the memory location specified by the operand. Example is STA 2000H, the location. Then you have STAX, that is store accumulator indirect. The contents of accumulator are copied into the memory location specified by the contents of the register pair. It's a 1 byte instruction. STAX-B. Then SHLD, store H and L registers. Store H and L registers direct. Operand is 16-bit address. The contents of register L are stored into memory location specified by the 16-bit address. The contents of register H are stored into the next memory location. 3-byte instruction. SHLD 2550H is an example. Then XCHG, exchange H and L with D and E. Operand, no operand. The contents of register H are exchanged with the contents of register D. 1 byte. The contents of register L are exchanged with the contents of register E. So the example is XCHG. Then first were the data instructions, and then second category is arithmetic instructions. These instructions perform the operations like addition, subtraction, increment or decrement. Addition, any 8-bit number or the contents of register or the contents of memory location can be added to the contents of accumulator. The result, that is sum, is stored in the accumulator. No two other 8-bit registers can be added directly. Example is the contents of register B cannot be added directly to the contents of register C. How it is to be used, how this instruction is to be used? ADD, add. Operand is RM. Description is add register or memory to accumulator. The contents of register or memory are added to the contents of accumulator. The result is stored in accumulator. 1 byte. If the operand is memory location, its address is specified by H-L pair. Example, ADD or add B or add M. ADC is next instruction. Opcode is ADC. Operand is RM. Add register or memory to accumulator with carry. So that C stands for carry. The contents of register or memory and carry flag are added to the contents of accumulator. The result is stored in accumulator. If the operand is memory location, its address is specified by HL pair. All flags are modified to reflect the result of the addition. Example is ADCB or ADCM. Next instruction is ADI. Operand is an operand is a 8-bit data. It adds immediate to accumulator. The 8-bit data is added to the contents of accumulator. The result is stored in the accumulator. 2 bytes are required. All flags are modified to reflect the result of the addition. Example is ADI 45H. Then ACI is the next instruction in the arithmetic instruction sets. ACI operand is 8-bit data. Add immediate to accumulator with carry. The 8-bit data and the carry flag are added to the contents of accumulator. The result is stored in accumulator, 2 bytes. All flags are modified to reflect the result of the addition. Example is ACI 45H. Next instruction is DAD. Opcode is DAD. Operand is register pair. Add register pair to HL pair is the description. The 16-bit contents of the register pair are added to the contents of HL pair. The result is stored in HL pair. If the result is larger than 16 bits, then CY is set. No other flags are changed. Examples is DADB or DADD. Next instruction set is related to subtraction. Any 8-bit number or the contents of register or the contents of memory location can be subtracted from the contents of accumulator. The result is stored in the accumulator. Subtraction is performed in 2's complement form. If the result is negative, it is stored in 2's complement form. No 2 other 8-bit registers can be subtracted directly. Example is the instruction SUB. Subtract related opcode is SUB. Operand is R and M. Subtract register or memory from accumulator. The contents of the register or memory location are subtracted from the contents of the accumulator. The result is stored in accumulator. It consumes 1 byte. If the operand is memory location, its address is specified by HL pair. All flags are modified to reflect the result of subtraction. Example is sub B or sub M. SBB is the opcode. Next opcode, operand RM. Subtract register or memory from accumulator with borrow. The contents of the register or memory location and borrow flag are subtracted from the contents of the accumulator. The result is stored in accumulator. If the operand is memory location, its address is specified by HL pair. All the flags are modified to reflect the result of subtraction. Example is SBBB or SBBM. The next instruction is SUI. Opcode is SUI. Operand is 8-bit data. Description is subtract immediate from accumulator. The 8-bit data is subtracted from the contents of the accumulator. The result is stored in accumulator. All flags are modified to reflect the result of subtraction. Example is SUI 05H. Then SBI. Operand is the 8-bit data. Subtract immediate from accumulator with borrow. The 8-bit data and the borrow flag subtracted from the contents of the accumulator. The result is stored in the accumulator. All flags are modified to reflect the result of subtraction. Example is SPF5H. Then the next instruction is related with increment or decrement. The 8-bit contents of a register or memory location can be incremented or decremented by 1. The 16-bit contents of a register pair can be incremented or decremented by 1. Increment or decrement can be performed on any register or a memory location. The example, the instruction is INR. It is related to increment, INR. Operand is RM, increment register or memory by 1. The contents of the register or memory location are incremented by 1. The result is stored in the same place. If the operand is a memory location, its address is specified by the contents of HL pair. Example is INR B or INR M. Next instruction is DCR, that is opcode is DCR, operand is R and M. Decrement register or memory by 1. The contents of register or memory location are decremented by 1. The result is stored in the same place. If the operand is a memory location, its address is specified by the contents of HL pair. Example is DCRB or DCRM. Then DCX, operand is R, decrement register pair by 1. The contents of register pair are decremented by 1. The result is stored in the same place. Example is DCXH or DCXB or DCXD. The third set of instructions is logical instructions. These instructions perform logical operations on data stored in registers. Data stored in registers or memory or status flags. The logical operations are, we already seen these logical operations: AND, OR, XOR, rotate, compare, complement. We'll see each one separately. AND, OR, XOR. Any 8-bit data or the contents of register or memory location can logically have AND operation, OR operation, XOR operation with the contents of accumulator. The result is stored in the accumulator. Let us see. Opcode is ANA, operand is RM, description is logical AND register or memory with accumulator. The contents of the accumulator are logically ANDed with the contents of register or memory. The result is placed in the accumulator. If the operand is a memory location, its address is specified by the contents of HL pair. SZP are modified to reflect the result of the operation. CY is reset and AC is set. Example is ANAB or ANAM. Next instruction is ANI. Opcode is ANI. Operand is 8-bit data. This description is logical and immediate. The I represents immediate with accumulator. The contents of the accumulator are logically ANDed with the 8-bit data. Result is placed in the accumulator. Example is ANI 86H. Next instruction is ORA. Opcode is ORA. Operand is R and M. Logical OR register or memory with accumulator. The contents of the accumulator are logically ORed with the contents of register or memory. The result is placed in the accumulator. If the operand is a memory location, its address is specified by the contents of HL pair. Example is ORAB or ORAM. Then we have the next instruction as ORI. Opcode is ORI. Operand is 8-bit data, logical or immediate with accumulator. The contents of the accumulator are logically ORed with the 8-bit data. The result is placed in the accumulator. Example is ORI 86H. Next instruction is XRA. Operand is RM, logical XOR register or memory with accumulator. Example is XRAB or XRAM. Then you have XRI immediate. Then you have the next set of instructions as compare. Any 8-bit data or the contents of register or memory location can be compared for equality, can be compared for equality, can be compared for greater than, can be compared for less than with the contents of accumulator. The result is reflected in status flags. Now what is the instruction? Opcode is CMP for compare. Operand is RM. Compare register or memory with accumulator. The contents of the operand, register or memory are compared with the contents of the accumulator. Both contents are preserved. And you have CPI, compare immediate with accumulator. The next group of instructions is rotate. Each bit in the accumulator can be shifted either left or right to the next position. Rotate, RLC, operand is done. Rotate accumulator left. RLC, rotate accumulator left. Example is RLC. Then RRC is rotate accumulator right. Then RAL, rotate accumulator left through carry. That is RAL. Then RAR, rotate accumulator right through carry. Then the next group of instructions is complement. The contents of accumulator can be complemented. Each 0 is replaced by 1 and each 1 is replaced by 0. That is called as complementary operation. The opcode is CMA. Operand is done, complement accumulator. The contents of the accumulator are complemented. No flags are offered. Example is CMA. A equal to A dash. Just they give the complement of each other. CMC complement with carry. STC, this carry flag, the STC is a set carry. The carry flag is set to 1, no other flags are affected. Then branching instruction sets. The branch group instructions allows the microprocessor to change the sequence of program either conditionally or under certain test conditions. The group includes jump instructions, call and return instructions, restart instructions. Now in my logical representation, wherever I have these sequence of instructions which have logical consequences, there these branching instructions will be of much use to me. So the opcode is JMP, operand is 16-bit address, description is jump unconditionally. Then JX is jump conditionally, jump conditionally. So we have jump if carry, JC, jump if no carry, JNC, jump if 0, JZ, jump if no 0, JNZ, jump if parity even, JPE, jump if parity is odd, JPO. Then the next instruction is call. Opcode is call. Operand is 16-bit address. Call unconditionally. The program sequence is transferred to the memory location specified by the 16-bit address given in the operand. Before the transfer, the address of the next instruction after call, the contents of the program counter, is pushed onto the stack. This is a call instruction, call conditionally. Now this is the set of opcodes we need to remember while calling with conditions. The opcode RET is used to return unconditionally. Now calling and returning, right? Giving back. The return sequence, the program sequence is transferred from the subroutine to the calling program. The 2 bytes from the top of the stack are copied into the program counter and the program execution begins at new address. Return conditionally, we have set of codes for return with conditions. Then RST, restart with software interrupts. The RST instruction jumps the control to one of the 8 memory locations depending upon the number. These are used as software instructions in a program to transfer program execution to one of the 8 locations. RST1, RST2, etc. Then control instruction. The control instructions control the operation of microprocessor. So NOP is the opcode. No operation is performed. The instruction is fetched and decoded, but no operation is executed. Then you have opcode, control opcode for control instructions. HLT, description is halt. Then DI, disable interrupt. EI, enable interrupt. RIM, read interrupt mask. SIM, set interrupt mask. This is how some of the instructions we have seen, and I just have given some sample assembly programs for simple arithmetic operations. This is the assembly program to multiply a number by 8. Now this is the instruction set. When you come back to college, I'm trying to take help of ENTC faculty members to execute these programs and have a video based on the usage of instruction sets, how the peripherals on the microprocessor 8085 are to be used, and how these simple operations can be executed. There is one more assembly program to find greatest between 2 numbers. So equal to, greater than, or less than. All these things can be done by using these instruction sets. So these were the few instruction sets we discussed. We also saw some of the pin diagram details. We saw some of the block diagram representation of microprocessor 8085. As I said, we are just having an overview of microprocessors. You need to read good textbooks. You've got number of text material available. I have put it on our Google Classroom. Even you need to go through it, and if you really are interested in doing some mini projects based on usage of microprocessors, you can always contact our expert faculty from ENTC department. Thank you for watching. Thank you, friends.